As we move now in earnest into the third part of our course, let's just call back to mind a little bit of what we learned about wave packets, because there's something very interesting going on here that can lead us to our first real semi-qualitative or semi-quantitative conclusion. And this has to do with our discussion where you will recall the idea was for correspondence to occur, I might have some classical particle moving on my x-axis here, and maybe it's decelerating, so they're getting closer together, each of the different time snapshots. The idea for this correspondence is that I want the probability that I get by squaring my wave amplitude of my superposition, which I've written down for you here, and I need that probability to correspond very closely to the classical position of the particle. I need it to move around and track actually wherever that particle is at any given time, so that I would always observe very closely a position for my particle very close to what classical physics says it should be. And secondly, and this is what I want to focus on today, we also want this packet to be kind of narrowly focused on my moving particle, hopefully at some distances that I can show are extremely tiny compared to what we would have been able to notice in our classical physics studies. Now, just a quick review of the math. Remember, this is a standard superposition where I add up a whole series of weights of a standard traveling waves, kx minus, and this is how the frequency depends on k. This is our dispersion relation times time t, and we now know exactly what to choose for this, so that h nu equals the Hamiltonian. Then we will indeed get this tracking. But in terms of how localized this packet is, it's very interesting to think in detail. We need to think a little bit about the weights that we're using. Now, these weights in this superposition, of course, can be complex numbers, which in the complex plane would have an amplitude or length of their little vector, a of k, and also a phase phi of k, as we had discussed last time, in this case measured down from the real axis because of my choice of minus sign. What I really want to focus on today, though, is the behavior of this amplitude of k. Now, that amplitude is just the complex amplitude, right? The magnitude of the complex number w of my weight. And what we had said we should choose for this is a function that is tightly concentrated with some range, delta k, around the point k naught. What we then did is we used a stationary phase analysis of the resulting integral, and we learned in the method of stationary phase the condition that the total phase of the integrand, its derivative evaluated near your peak, should be 0 if I want to find the maximum contribution. So when this derivative is 0, what I'm actually getting is the value that corresponds right to the top of this peak here. Now, we also showed that definitely would give us the maximum contribution when all of our phasors are adding up in a perfect straight line. So maybe I'll give you like a diagram below. That's when they add up this way, all in a perfect straight line, at least in the vicinity near k naught. But there's an acceptable range where there might be some arcing around, and we just happen to pick 30 degrees, right? You'll definitely get a shorter contribution in this case, but it'll still be respectable. So when I put plus or minus 1 over 2 delta k, that won't give me the very maximum peak point, but it'll give me some point that is somewhat down off the sides of this thing, right? So ultimately, putting these values in for the phase, the total phase derivative, that will tell me ultimately how wide my peak is. So when we applied this equation, we learned the following. We could actually solve for the positions x within my peak, where the central peak position is given by x naught plus the group velocity times time. Right? So nice linear behavior in this particular case. But we also found that x corresponds to plus or minus, this term that we have, right? 1 over, delta x. I'm going to write it that way. I'm sorry. Plus or minus some range, delta x. And we could then read off from our stationary phase analysis what each of these constants were. The initial position has to do with the phase derivative of the weights near k naught. The group velocity has to do with the derivative of the dispersion relation near k naught. And finally, this delta x was given precisely by this term here. So what we see is that there seems to be some kind of a limit on things, right? There's a tension, it seems, between delta k here, delta k over here and delta x over here. Now, to unravel what that might mean physically in our physical world, it's helpful to understand what k actually represents. So I want to make a small note here now. So note, k, of course, as we know, is 2 pi over lambda. But as we know from Davis and Germer, right, and Compton, the wavelength lambda equals h over p. So what I find, in fact, is that k, the wave vector k, is directly proportional to the momentum, with a fundamental constant as the proportionality constant. So really, when I'm drawing this here as a function of k, you can think of this just as well, because it's just a simple constant scaling between the two quantities, as some amplitude here written out in terms of momentum. Now, the relation that I've given you, this way writing it's a little bit ugly. Sometimes we're more interested in going from our wave quantities to our more physical quantities like momentum. So it's useful also to write the momentum in terms of the wave vector. I just had to move these terms to the other side of the equation. I then have h over 2 pi times k. And it turns out that this combination, h over 2 pi, is going to come up quite a lot as we build up our formal theory. And the reason is that you see here, h is what's connecting wavelengths lambda to momenta, or frequencies nu, right, to energies. But when we start to write down formal wave physics, we don't think about lambdas much anymore. We think about wave vectors k. And likewise, we don't think about frequencies nu. We think about angular frequencies omega. And because there's always these 2 pi's flying around, it turns out that when we relate things like wave vector to momentum, as we're doing here, I'll always get this extra 2 pi. And likewise, when I turn angular frequencies and relate them to energy, there'll be another factor of 2 pi. So it turns out that there's a much more convenient combination of constants to use, which is, in fact, this h over 2 pi. So we give it a special name. It's called h bar times k, and you can write it as a script h or as a plain old h. It doesn't matter. The basic idea, though, is you put this bar on top to remind you of a divide by, right, 2 pi. So we're going to define a new Planck's constant. H bar is defined just as our usual 1h, but divided by 2 pi, just for convenience sake. Okay, now with that little aside out of the way, we want to start to begin to interpret what we mean by this delta k, right? This delta k, what it says is that the wave packet associated with my particle is built out of different wave vectors. They're concentrated about one particular wave vector, which is what we need, right? Because when they're concentrated around one particular wave vector, then we get a well-defined velocity for my particle. If they were concentrated around some other wave vector, I would get some other group velocity for my particle, right? And if my particle is going to, move around with a consistent velocity, I need to choose a narrow range of k near my central value of k naught. Now, what this means physically, though, and we can see it in our relationship here, is that if there is a range of k vectors like this associated with my particle, that means, in fact, there is a range of momenta associated with my particle through this relationship. So if I were to go and actually measure the momentum of my particle, I'm not guaranteed that I'm going to get k naught or h bar times k naught. Instead, I could get a range of momentum associated with the range of this peak. So my particle itself, what this is really telling me, if I went and measured its momentum, because it's associated with a range of momenta in order to make this superposition to construct such a wave packet, there is a range of momenta I could measure for my particle. So that's kind of my key conclusion here, is the particle is associated, at least in this wave packet picture, right, with a range of momenta. Now, hopefully, we can make it small because we're not used to our particles in classical physics having a range of momenta. They just have one momenta. But notice we can't make it too small because if I make this peak too narrow, delta k would become 0, and if delta k goes to 0, that means my wave packet is rather wide, right? I then have an uncertainty in where exactly I'd be measuring the particle. There becomes a spread there. So there's some kind of fundamental limitation here. So our particle is associated with a range of momenta, delta p, right? And because p is just h bar times k, the range in p is just h bar times the range in k. So delta p equals h bar times delta k. What our other conclusion is from our discussion here is that there seems to be a limit. There is a fundamental limit on how precisely we can define the location x and momentum p. And technically speaking, we are just talking about motion right now in one dimension, right, along the x direction. So just to be precise, in the location x and the momentum p, right, in that same direction. And that fundamental limit on how precisely we can define them is that this product here, delta x times delta p, seems to be something that we can't quite make to go to 0 because we know that delta x delta p is delta x times h bar delta k. But we had seen up above here, right, that delta x is 1 over 2 delta k. So that would be 1 over 2 delta k. That's my delta x. Then I have h bar times delta k. And interestingly, my delta k's cancel out, and I get a quantity. And I should stress, I should write this as approximately, right, h bar over 2. And why I say approximately is I want you to notice we haven't put yet any very precise meaning on how exactly we measure the width of this peak or the width of this peak, right? Where this is really more of an order of magnitude thing. And tied into that is, you might recall that I had kind of arbitrarily chosen 1/2 radian of bend here for getting sort of how far I am down the side of my peak. That was an arbitrary choice I had made also. So this is sort of order of magnitude description of what's going on, but it shows you that fundamentally, if I try to make my momentum very well defined, right, I end up with a very wide spread in my particle, but this product itself, it seems to be associated with my fundamental constant. So through this argument, then, we can begin to come to a new fundamental principle. And that's really the main topic I want to discuss here in the present lecture, right? And that is something known as the Heisenberg, and that's what that relation reflects, the Heisenberg Uncertainty Principle. Now, because that's a lot of writing here on the screen, right, or on the board, I like to abbreviate things, so I'll be calling that HUP, right, Heisenberg Uncertainty Principle. And what this principle states is the following. After any measurement, it's usually thought of traditionally in terms of measurement. So I'm giving you a traditional statement of this principle. And we will work through some examples where you can see how we think of this in terms of a measurement. But after any measurement, right, the position x, right, and corresponding momentum and that corresponding momentum is of course P of x, will be left uncertain. And now I'm going to specify for you precisely the sense of that uncertainty. They will be left uncertain in the sense that precise follow-up measurements so we're going to measure something like the position of the particle, but then we're going to do a precise follow-up measurement. And I guess I should specify precise immediate, right? Because this is fundamental. It's not like, oh, things will just drift around later. But precise immediate follow-up measurement will yield ranges of results so it won't be necessarily exactly what it is that you think you just determined. There's going to be a range if you test it, again, with an immediate follow-up measurement. And they're going to lead to a range of results in both, actually, x and the momentum. So the ranges of results I will call delta x. And that's the term we give to it. But what it precisely means is the standard deviation of x that you find in those follow-up measurements. So this is standard dev in the follow-up measurements. And there's also going to be a range in the follow-up momentum measurements, delta px. And what I mean, again, precisely, is there will be a standard deviation in that range. There will lead ranges of results, which can never be more narrowly defined. So more narrowly defined than, and there's actually, if you get very mathematically precise, a very precise answer for this. Notice again, here we gave an approximate argument, right? So, but we didn't have precise definitions for delta x and delta p. So you have to take this as sort of this kind of semi-quantitative or qualitative analysis of the situation. What I'm telling you now is the actual precise statement. This is what we will be able to make once we have a strictly, fully formal theory. So right now, I'm going to give you some qualitative descriptions of this type of phenomena. And I promise you later, we will be able to get quite quantitative. So I'm really writing you an IOU that we will come back and make these things extremely quantitatively precise. But for now, I would just like to do this at a qualitative level so we can get a good understanding of what, an intuition of what these results actually mean. So no more narrowly defined than this product delta x, delta p sub x is always going to be strictly, well, it could be equal, so it's always going to be greater than or equal to this fundamental combination of constants, h bar over 2. That is the formal statement of the Heisenberg uncertainty principle.